Hello, AP Calculus students. It's time for the Chapter 3 review, which we started today in class. The answer document from CPM published is already in Google Classroom waiting for you. So, what we're going to do is we're going to work through as many of the problems right now that we didn't do in class as we can. It might take 20 minutes, it might take 30 minutes. I don't know how long this one's going to be. Haven't previewed the questions, but we can at least walk through some of the ones we've already done so far. Question 1, what you're going to want to do is you're going to want to basically find the slope between the point where x is 0 and the point where x is 0.8. That's what we did over here. For the next part of the question, we don't have enough information in this table to find the exact instantaneous velocity, but if we want to estimate it, we can use points that are equidistant from it on either side. So that's why I chose 0.2 and 0.4 and 0.6 and 3.7. Again, just using the slope formula to figure out the rate of change there between those points, and you get about 8.25, which is the answer. Question 2, just be aware of what positive and negative and zero slopes look like. For example, at point D, it's pretty positive, but not as positive as is point A. That's why I know that D is probably 1 and B and A is probably 3. Question 3 is just using some power rule to arrange some things around. Not really a huge deal there. I'm not super worried about those. You can pause this video at any point if you want to look at more of the notes that are here. Number 4, this is rewriting these as using exponents and then using the power rule, a very powerful topic in AP Calculus. Let's see. So in red, I have gotten the rearrangement based on, or in power rule, or sorry, in the fraction form, and then in black, I got the derivative. Looks like I didn't do C. F prime of x in part C would be 5 times 4 would give us 20, and 20 over 3 would be the fraction in front, and we would have x to the 1/3 power dropping down 4/3 by 1 right there. Again, I'll zoom out a little bit on those and let you just ponder the answers to those. For question 5, this is a simpler version of what we did on the big story problem yesterday and a little bit today. Again, what you're going to need to do first is plug into the original function, because you need to know what y is when x is 2. Looks like it's 12. So the point 2, 12 is where we're going to find the tangent line. Next, you need to find out what y prime of 2 is. So first you got to find y prime, which I did over here. There's your original function in green. Y prime is in blue. Once you got y prime, you got to plug in 2, which unfortunately is not a whole number, and that's just going to be what it is. I rewrote the 12 as 36 over 3, and then subtracted across to get 34 over 3. This is the slope, because y prime tells you what the slope is. That might be, you think about it as m in your traditional slope-intercept form. And that's exactly what we did. Now that we know that the slope is 34 over 3, we can take point slope form and plug in all the relevant parts. Y minus 12 equals the slope times x minus 2. And that's it. Don't need to go any further. Question 6 says that a certain function has a slope of 0 at exactly 2 points. Really, when we say slope of 0, we need that y prime be 0. So we find y prime. We plug it, we set it equal to 0. We solve it and get -2 and -3. Then, kind of a lengthy process here with some nasty variables and nasty decimals and fractions, but overall pretty simple. We plug in -2 and -3 into the original function to find the y value at those points. Neither one of them is very nice, but there they are. Again, you can work through the steps there if you want to. Pause this video to see the actual work that's going in there and take a look and work through it step by step. Common practice, if they ask you to find the point, you got to find the x and the y. Let's see. Question 7, I did cross off B and C on this because, holy God. Anyway, A's not too tough, though. I did take the original problem and rewrite it a little bit. I took 1 over 3x squared and kept the 1/3 out in front and took x to the -2nd power. And then taking the derivative was relatively easy to do over here. For question D, it looks like that's kind of where I left off on this problem. So I'm going to do D over on the space into the right here. I'm starting to recommend more and more as we do this that you guys have a blank paper somewhere, because some of these problems are kind of lengthy. And you want some more room than what I've given you for a lot of them. So for question D, we're looking for the derivative of, let's rewrite our original function. First thing I'm going to do is I'm actually going to expand out this expression. We'll have 3x times x squared is 3x to the third. 3x times 1 is minus 3x. 3x times 3x is plus 9x squared, and negative 1 times 3x is minus 3x. So I'm expanding all that out. Probably a helpful thing to realize that we're going to have, well, it looks like if I did that right, third. Oh, did I do minus 3x twice? Oh, I missed one. Sorry, I made a mistake. It should be minus x squared right there. Cool. That's why I should preview questions before I do them, but that's okay. Now that we got this kind of arranged, well, we can combine together our forces of negative x squared and 9x squared. So we're looking for the derivative of 3x to the third plus 8x squared minus 3x. And we're going to go ahead and run this through the power rule. It'll be 9x squared plus 16x minus 3. Bada bing, bada boom. Simple. 8 is actually really easy to do. We started this one kind of at the end of class today. This is starting to see if you can recognize in the structure of the original f prime of x definitions what the original function is. If you have the h approaches 0 version of this, it's f of x plus h minus f of x over h. But see, the key is the f of x part, the original function. That's how I know the original function in A is 2x squared plus x, and the original function in C is x to the negative second power. Those are easy to take the derivative of once you can pull them off of the limit definition of a derivative. Kind of the same thing for B and D, but B and D both use the other version of the derivative formula, where it's the limit as x approaches c of f of x minus f of c over x minus c. Here, f of x is hanging out in the front, 4x squared or the square root of x plus 3. Once you can recognize where f of x is, now it's really easy to pull that off of the equation and then run it through the power rule. Over here in question B, f prime of x would be 8x. And in question D, probably a good idea to rewrite that as x plus 3 to the 1/2 power, because then you can run it through the power rule. F prime of x now is going to equal 1/2 in front times x plus 3 raised to the negative 1/2 power, which you could then rewrite by taking that negative square root thing, moving it all to the bottom of the fraction. 1/2 times the square root of x plus 3. The more we practice this, the more you get used to dealing with big math problems that have lots of different chunks and the thought process involved there. So keep your confidence up as you work through these. We're kind of attacking everything from all fronts with this curriculum. We're both doing the formulas and also seeing problems that get a little more complicated as we go. So keep it up. You guys are doing a good job. And don't worry about your grades so much as just keeping up with the work. That's all I ask. Question A, explain what's happening between 2 and 4 for T. Here we have a velocity graph. A bug crawls in a straight line according to the velocity graph in meters per second. So here, the velocity is constant, which means he's moving at a constant, looks like -2. So I would say on this range, he's traveling at -2 meters per second. The velocity is constant. As far as calculating the total distance in part B, what we want to do there is find the area under the curve. That's kind of the challenge here. There are a lot of different ways to divvy up this area, but let's just break down some of the easier ones. I'd like to think about this whole chunk there as one big trapezoid. It's got a, let's see, one base is going to be 1, 2, 3, 4, 5 wide. The other base is 1, 2 wide, 5 and 2. And it's got a height of 2 also. So the area of that trapezoid is 1/2 times base 1 plus base 2 times the height. 1/2 and 2 cancel out there, so this is 7. Just going to remind you that it's -7 inside of that because it is underneath the x-axis. Let's see, the next chunk might be this little piece right there. I might divide that up. Again, there's different ways to do this, so pick whatever you want. Like maybe you recognize this little triangle right there. That might be easier too. That triangle is a 1/2 right triangle. So the area is 1 times 2 divided by 2, which is just 1. It's a positive 1 in there. Next, you have a 2 by 2 square. That's going to be 4. And, next you kind of got this little area here is going to be a mess no matter what we do. So I'm going to chunk it into a trapezoid and a right triangle. The trapezoid right there is going to be 1/2 times, this time I'm thinking about the bases being vertical. Looks like I have a base of 2 and a base of 4, so 2 plus 4. And the width is 1 times 1, which is just that right there. So that's going to be 6 divided by 2 is equal to positive 3. You know what's cool about this is so far we got a balance. We have negative 7 down here, and we have positive 7 up here in those three. So basically the area under the curve is just going to be whatever's left. That's a right triangle with one side is 1, one side is 4, and then it's divided by 2. It's going to be 2 right there. So if you add it all up together, we're going to get a total area under the curve of 2. So the total, actually, hang on, I got to read the question correctly. Total distance means we don't care about negative or positive. So the total distance is going to be 7 plus 1 plus 4 plus 3 plus 2. We're going to add it all together with absolute values involved. So that 7 plus 7 is 14 plus 2 is 16 meters. How far does the bug end up from his starting point is the other question. Now we do care about negative and positive. He's traveling to the left 7 and then to the right 9. So he's going to end up 2 meters, a positive 2 meters, to the right of his starting point. As far as when the bug's velocity, we got to think about this one. Velocity is what you see on this graph. So when is it 0? Let's see. I don't know. There's a lot of drawing on this space right now, but I'm going to keep trying to keep it. I'll do orange for this maybe. The velocity is 0 right there at 1, 2, 3, 4, 5. And then again at 6, 7, 8, 9, 10 right there. So 5 and 10 are the places where the velocity is 0. Greater than 0 is going to happen, let's see, actually there's only basically one range where it's greater than 0 and one range where it's less than 0. It's greater than 0 from 5 to 10. And I'm putting those in parentheses because I wouldn't say it's positive at 5 or at 10, just in between those numbers. The velocity is negative from 0 to 5, like this. Next, we have when is the bug's acceleration 0 or positive or whatever. Might be useful to make a little sign chart for this one because remember, acceleration is the derivative of this graph. And so if this graph is decreasing, its derivative, or the acceleration, will be negative. If the original graph is increasing, then the derivative will be positive. So let's kind of break this up into chunks. I see negative 2, there's a change. Positive 2, what am I doing? Positive 2, there's a change. Positive 4, there's a change. There's a change again here at 6. And a change, a change again at 8 and then 10. What we're looking for here is when the graph is increasing or decreasing. Let's do decreasing first. I'll highlight these in green. This graph is decreasing on this range and then again on this range right there. So that means that our acceleration will be negative on that range and again from 8 to 10. From 0 to 2 and from 8 to 10. I'm going to go ahead and put those down right now. 0 to 2 and 8 to 10. Maybe put a union in between these like that. That's where it's negative. The next thing I see is it's staying 0. It's 0 from 2 to 4 and then again from 6 to 8 right there. Actually, I kind of messed up. There's a change. Sorry. I apologize for this. There is a change again at 9, isn't there? I'm going to edit my answer from earlier. It's negative here. 9 to 10. Because it's positive from 8 to 9. I see it now. I would say it is exactly 0 from 2 to 4. And then again from 6 to 8. And as far as when the graph is positive, I'll highlight that in yellow. It's positive on this range and that range. That's when the acceleration will be positive because the velocity is increasing. That's the connection there. That's happening from 4 to 6, and then again from 8 to 9. 4 to 6, 8 to 9. At what time does the bug pass over its starting point? That's going to happen. Well, see, if you think about the motion of the bug, it starts here at 0, and then it moves to the left 7 spaces, indicated by the negative 7. Then it goes back to the right, and it crosses 7 spaces after 1, 4, and 3. That's not 7. Ah, shoot, that's a tough question to answer. Have I been doing this math wrong the whole time, too? I think I made that mistake. Oops. It's 1, and it's 4, and it's 3. Let's see, that is 3. That trapezoid is 3. So it moves to the left 7, and it goes back to the right 3. I got to change some of my numbers from earlier because I can't add to save my life together, apparently. The total distance traveled is going to be 7 plus 1 plus 4 plus 3 plus 2, which is not 16. It's going to be 8 plus 4 is 12. 12 plus 5 is 17 meters. Which means this answer here is 3 meters to the right. I apologize for that. Oopsie. As far as what time the bug passes over its starting point, let's see. It goes 7 to the right. It's going to be hard to pinpoint the exact time that happens because I believe it's going to happen somewhere in between 8 and 9 because it goes 7 to the left, but then it's going to start moving back to the right, and it happens somewhere in here because 1 and 4 is 5, so you have 2 more to go, and it happens somewhere between 8 and 9. So I'm just going to say T between 8 and 9, somewhere in there. I actually don't know. I wonder what I'm going to take a quick look at what the actual published answer guide says, which I did publish in your Google Classroom. 8 says, oh, this is the actual, oh, here it is. 7 plus square root of 3, I'm not solving that. Pucky, I'm not doing that. That's no need. Don't worry about F. Cross off F. I hate it. Dumb, dumb, silly, dumb. Not necessary. Somewhere between 8 and 9 is just fine. I like that answer a lot better. Okay, moving on. Maybe did I count that right? 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Yeah, okay. Anyway, I'm over it. Okay, move on. Question 10. Given f of x, sketch f prime of x. Okay, so we got to think about slopes for a minute here. So in question A, the slope of this line, always negative, constant rate. We don't really have any numbers to go by here, so any negative horizontal line will do just fine. Something like that. That would be f prime of x. Question B, we have a slope that is steadily decreasing. I think what's important to notice is that this is positive here, it's 0 here, and then it goes negative there. The slope itself starts positive, hits 0 right about there at the maximum, and will continue to decrease. So a linear line decreasing through that point is just fine for the slope of this graph. Question C is going to start off really close to 0. Looks like the slope is 0 right about there. It's never going to be 0, but it's going to start off. And it looks like the slope is just kind of continually increasing. Honestly, the slope graph of this will actually really mirror the function. This is a concept that we'll talk about later on. This is going to start off this, and it's probably going to be pretty close to the actual original function. We'll talk more about this later on, but the graph of e to the x has the derivative of e to the x. This is, I believe, trying to illustrate this point that the derivative of exponential functions is often also exponential. So, just like that. Question 11. Sketch a possible graph for the function given the information below. So we are going to sketch a graph who is increasing from -2 to 1. We're going to sketch a graph that has this point on it, -2, -3, sorry. It's going to have the point 1, 4 on it, and it's going to be decreasing on the rest of those ranges. So let's go ahead and make this sketch happen. It seems pretty easy to me. We're going to go back 2 and down 3 to go right there. We'll go to the right 1 and up 4 to go right there. Those 2 points got to be on the graph. And then we have to have an increasing from -2 to 1, which kind of has to happen anyway, and decreasing everywhere else. So the graph should look something like this. Decrease to that point, increase to this point, decrease after that. That'll do. Pretty fine. Use the formal definition of a derivative to find f prime. Don't do that. Why would you do that? Don't do that. Use the power rule. 6x minus 2. Unnecessary. 13. A ball is thrown straight up into the air and its height is determined by the equation h of t. Height in there. Let's see. Okay, so this is a classic calculus question. We know the height function. We want to know when the ball reaches its highest point. If you think about this graph right now, you could graph it really quick on a calculator. It'll be a parabola, and its highest point will be right kind of in the middle. As far as finding it, what we're going to do is we're going to take the derivative. We're going to find h prime of t, and we're going to figure out when that equals 0. That will tell us where the maximum point is. So let's do that. This is for part A. H prime of t is going to equal negative 32t plus 15. Pretty straightforward. Whoops, give me a calculator cam out of the way. We want to know when this equals 0. So, if we subtract 15 and then divide by negative 32, that will tell us the answer, which will not be a nice answer, but it will be an answer. 15 divided by 32, whoops. Looks like it's 0.46875. I'm going to just use that decimal for the rest of today. In fact, for a calculator-heavy question like this, I would recommend that we just keep that number right there because we're going to use it by using the calculator's recall features here. So that happens at t when it reaches its highest point is at t equals 0.46875. This is not the same question as asking how tall it is, but we'll find that in a minute here, I suspect. Actually, no, I'm reading the question. Next question is, what is the velocity of the ball at t equals 0.5 seconds? For this, we're just going to plug in, velocity. We're going to use our newly found h of t. Or sorry, h prime of t, because h prime of t is the same thing as the velocity, v of t. So for part B of this question, we are going to find what v of 0.5 is. And I think we're going to use the calculator for that. We're just going to do negative 32 times 0.5. And we will add to that 15. And we get 175 for an answer. What that means, as far as that second part of the question goes, it's a positive number. So that means that the height is increasing at that time. Just really hang on, I gotta think about this, make sure I got that correct. 32 times... Oh, I see what I did wrong now. I'm like, that's way too big. Hang on. I was like thinking that is way too big. It's negative 32 times 0.5. I typed negative 5. There we go. 16 plus 15. Much better. Negative 1. Okay, I was like, that doesn't seem right to me at all. My alarm was kind of going off. V of 0.5 is negative 1. Because this is negative, this means that the height is decreasing. It's decreasing by 1 meter per second, which makes sense because 0.5 is just after the time we determined was the maximum height. The height of the ball will increase, hit the top, and then start decreasing. That's kind of why my alarm was going off about that answer. Question C asks us, what's the acceleration of the ball? Well, all we got to do there is go one more level down. For question C, we're going to find A of t, which is equal to V prime of t. And what actually happens here, since V of t is equal to negative 32t plus 15, if you go one more level down in derivatives, it actually just becomes a constant number, negative 32. Technically, it's negative 32 feet per second squared, which is the acceleration due to gravity on planet Earth. So it should match in this problem. Question 14 says to evaluate the given limits. So let's just think about some limit questions for a hot second. Here we have a limit as x approaches negative infinity. x approaches infinity. So if you think about 3 to the negative infinity power, this is equal to 1 over 3 to the infinity power. So you're taking 1 and dividing it by a very, very large number. It's basically going to become 0. Question B asks us to plug in 49, limit as x approaches 49, which if we plug it in will give us 0 over 0, unfortunately. So we're going to use that old conjugate trick that we've seen a number of times to solve this problem. We're going to multiply by the square root of x plus 7 over the square root of x plus 7. This is going to give us the limit as x approaches 49 of, on the top we're not going to expand this out because part of it will probably cancel later. So we'll just leave those two factors alone. On the bottom, we're going to have x. I'm not going to write it down, but there will be a positive 7 roots of x and a negative 7 roots of x. And those will cancel out. And we'll also have a minus 49. And there's our factor that will cancel out from the top, which is why this method usually works. Because now we can find the limit as x approaches 49 of the square root of x plus 7, which is 7 plus 7, which is 14. There you go. For question 7, we're looking at the limit as x approaches negative infinity of this rational function. Normally, what we do is we take a look at what's going on with this number compared to this number. Because all that's really going to matter as we start plugging in very, very large negative values for x is that the only thing that will matter is x to the 8th and x to the 9th as they compare to each other, because these guys won't really matter at all. So we're just going to kind of ignore them for now. Now we really got to think about negative infinity to the 8th power divided by negative infinity to the 9th power. What's important here is that the bottom is going to be infinitely larger than the top. So no matter what, we're approaching either 0. Well, we're approaching 0. It won't actually matter. I think it might be worth pointing out that the top is always going to be a positive number because it's a negative thing. But it really won't matter because this number on the bottom is going to be so much larger. That's the word larger. Let me try that again. So basically, for the same reason that part A is 0, C will also be 0. The only difference, I suppose, is since it'll be a negative number, it's going to approach 0 from underneath instead of approaching it from above. That might be something to think about there too. But let's move on. We're in the home stretch here. Question 15, again, here you got your original graph. Let's sketch double prime of x. Ooh, interesting. We're looking for a concavity graph. So here, we're going to take the graph and make an understanding about its concavity. For example, in question A, the concavity is always up. It's always concave up. So any straight line, horizontal, positive line will do for the concavity here. Here, the concavity is switching. Looks like this is a sine wave. The concavity is switching at these points that I'm marking along the graph. Those are your points of inflection. So as long as, and it's up here and down here. Up and then down and then up. So we need a graph that is positive and then negative and then positive and then negative and then positive again and crosses 0 at these points. So right underneath that, we'll put some zeros down. And let's just make a graph that kind of mirrors what this is doing, but just tracking the concavity. That'll work. That works pretty nicely, in fact, I think. This is kind of mirroring the idea that when you take derivatives of sines and cosines and just sines and cosines, you keep getting sines and cosines. Here we have a graph that is concave down and then concave up. And there's only one point of inflection. So we'll put a 0 here, and honestly, any linear graph that comes up and does this, that will do the trick pretty nicely. Concave down is negative, concave up is positive. That's the concept. 16, use the formal definition of derivative to find h prime of x for x squared minus 1. Then find the equation of the line tangent to the curve at x equals 9. I'm not interested right now in doing more problems about the formal definition, so don't worry about that. But I do want to find h prime, and I do want to do the rest of this problem. So let's do that. First thing we're going to need to know is what h prime of x is, which we can find right now is just 2x. Now for this problem, we need the point and we need the slope that we're at. Now, of the point, we currently know the 9. We know the x value is 9. But what we need to know is what the y value is at 9 also. So what we require is h of 9. We're going to plug 9 into the original function. This will be 9 squared minus 1. 81 minus 1 is 80. And that's going to go in the y slot of our point. So these are the points that we're going to use in point slope form of a line in a moment. We also require the slope, which we can get from the derivative function, h prime of 9, which is going to be 2 times 9, which is 18. So what we'll do now is we'll actually start building our point slope form. It goes like this: y minus f of a equals f prime of a times x minus a. In this problem, a was given to us as 9. We found f of a to be 80, and we found f prime of a to be 18. So all we really got to do is plug these numbers in, and then we're done. Y minus 80 equals 18 times x minus 9. There you go. Don't need to go any further than that, by the way. I wouldn't recommend going any further. Don't need to. 17, we got another one of these sketch a graph that it has all the properties listed below. So here we go. Let's start by thinking about this. We need an asymptote at y equals 2, at least on the left side of things. On the right side, we need an asymptote at y equals 0, because that's positive infinity. The graph has to be completely continuous, and it has to contain the point 0, 5. Seems pretty easy enough. Let's make it happen. So let's put our point down, 1, 2, 3, 4, 5, put it right there. We have a graph that's going to have we need a left-handed horizontal asymptote at 2, so we'll go ahead and just kind of sketch a curve. It does something like that. And then it's going to approach 0 as time goes by on the right side, so maybe something like that. There you go. That's all you got to do. 18 asks us to thoroughly investigate the graph of f of x equals 2x to the third minus 10x plus 4. When you talk about increasing, decreasing, concave up, concave down, and points of inflection. So let's actually do that. It's actually not too tough to do. Let's start with our original function. This is for 18 over here. I'm going to do all my work in a blank space. I suggest that you do the same. We got 2x to the third minus 10x plus 4. Really common, very powerful AP Calc thing to be able to do. The first thing we want to do is take a look at f prime of x. F prime of x will tell us where it's increasing and decreasing. So we actually could right now, and let's just do this for fun, we'll graph it. 2x to the third minus 10x plus 4. Push that graph, and there it is. I could adjust the window a little bit to see it, but you can get a good idea what's going on right now. But we're going to do this analytically by looking at the derivatives. F prime of x will be 6x minus 10, like that. Next, we need to know where it's increasing and decreasing. So usually, 6x squared minus 10, Ford, come on, get with it. 6x squared minus 10. If we want to know where it's increasing, decreasing, we got to know where this is positive and negative. So we'll do that next. First, let's start by finding where it's 0. Because once we know where it's 0, then we can really break down where it's positive and where it's negative. So this is going to happen when 6x squared minus 10 equals 0. You could factor a 3 out of that, I suppose, but it doesn't matter. 6x squared equals 10. X squared is going to be 10 over 6. That's not a nice answer, by the way. Yikes. Ugh, that's not fun. X is going to be the square root of, I'm going to say this is 5/3, square root of 5/3. And what we should note is that it's going to be plus and minus, which might be helpful on the calculator. Just get a quick estimation of those. Square root of 5/3. It's about 1.29. Plus and minus 1.29. Now, how that's going to help us, that tells us where the original graph has horizontal tangent lines, maximums or minimums. So what we should do is kind of build a sign chart. Let's do that over here in this space. I'm going to scroll down a little bit so you can see it. This will be our f prime of x graph. And we kind of know that at negative 1.29 and positive 1.29, there's going to be a shift because those are the zeros that are there. You can kind of tell from looking at the original graph or by plugging in numbers into your f prime. Like, for example, if you plug in 0 right in the middle of there, you get a negative number. And If you were to plug in, say, I don't know, -2, you would get 6 times 4 is 24. 24 minus 10 is a positive number. And it'll be a positive number over here for the same reason. So what you're going to have is you're going to have positive and then negative and then positive and the switch at those negative and positive 1.29 points. So this graph is increasing and then decreasing and then increasing on those ranges. We'll put that together when we make the final sign chart in a moment. Next, let's take a look at concavity by looking at f double prime of x, which in this case is going to be 12x. That's it. Simple. This is 0. F double prime of x is equal to 0 when 12x equals 0, and that happens when x is 0. So what happens here, f double prime is much simpler. Right there at 0, you have kind of a switch from negative to positive, and everything is negative before that and positive after that when it comes to f double prime. And that tells you the concavity. So what's going on here? Let's look at our f of x, and we'll kind of break it down analytically by putting every kind of spot where there's a switch. We're going to put that down. We have negative 1.29, we've got 0, and we've got positive 1.29. And here's what we kind of know by looking at this little chart that we've built. We know that on this first little range here, we know that the graph is increasing and concave down. Then we know that the graph is, from this little range right there, it's decreasing and concave down. On the next little chunk of the graph, it is still decreasing, but now concave up. And on the last little chunk right there, it's increasing again and concave up. Building a sign chart like this is a really powerful tool for analyzing a lot of different functions. This is a pretty simple one. You know, we could have looked at the graph right here a while ago and said the exact same things. You can see that increasing concave down, decreasing concave down, there's your point of inflection, decreasing concave up, and increasing concave up. But the derivatives help you see all those things in a kind of a different way. Let's look at, this video is getting kind of long. We're almost at 40 minutes. Yeesh. Let's look at 19 for a minute. We got to find antiderivatives for each of the following functions. So we got to think backwards about derivatives. Capital F of x. All you got to remember here is that the powers all go up by 1. So x squared becomes x to the third power because we're going backwards. And we got to think, okay, what do you multiply 3 by to get 3? And it's just 1. So that's fine the way it is. The next one is going to be an x squared, and you got to think, okay, what do I multiply 2 by to get -4? So minus 2 would work there. And you can put plus 5x down, and then put a plus c, and that'll do it. Just a pretty simple thing. You got to get used to doing antiderivatives and regular derivatives, going back and forth. For this one, capital F of x, which is the antiderivative, our -2 will just hang out right there. The derivative of cosine is negative sine. So actually, let's change that to a positive 2, and we'll make it the cosine of x. And we got to put a plus 1x there too, so that will become 1 when you take the derivative. And of course, plus c. Don't forget plus c. Question C, this might get a little hairy. I'm looking at the fractions going on right there. So it's a good idea to have in your head just kind of a good working knowledge of adding 1 or subtracting 1 from a fraction. We saw that back in the first few problems too. Here, capital F of x, you might have like, okay, let's have x going up by 1 would take 2/3 to 2/3 plus 1 would give you 5/3. And I don't like this question at all, but we got to kind of think about it. When we multiply 5/3 times something in front, we have to end up with 4/5. Yeesh. That is not a fun question to answer. I'm going to answer it algebraically, I guess. The best way to answer it is by multiplying 3 over 5, like that. So x would be, in this case, 12 over 25. That is absolutely insane, and I hate it. Absolutely bonkers. Why would you do this to high school students? Holy beans. I apologize. That's ridiculous. I think it's right, though. 12 over 25? Because you get 60 on top, 75 on bottom, and that is 4/5. All right. Okay, last question. Negative 1/2 going up by 1 would take you to positive 1/2. And kind of, again, we got to think, okay, 1/2 times what number would give us 1/7? This is a little easier to deal with. Just multiply by 2 on both sides. It'd be 2/7. There we go. Then the 2 and the 1/2 would cancel out, and you'd be right back where you were. Don't forget your plus c. That's a ridiculous problem. At least 4 different types of situations where a function is non-differentiable. Let's write 3 of them. How about a cusp, a sharp corner? How about a vertical tangent line like that? That would be a non-differentiable point. How about a point of discontinuity like this? That would be a non-differentiable section. And what about the good old classic, just a hole in the graph? That would also be non-differentiable right there. Pretty straightforward. I did not intend for this video to be 40 minutes long, but man, I hope you guys made it to the end. That's a lot of stuff. It is a good review of just about everything we've done up to this point, though. Try your best to stay as we go through this journey together. I know staying positive is oftentimes pretty tough. You guys are doing a great job just by being here. And remember that, even if you don't get every answer correct, every little thing you do makes you a little better every time. So try to keep those motivational things happening. You are doing a great job, and you are growing every day, and that's fantastic. And I'm really proud of you for making it this far. And I'll see you tomorrow. We're going to do the test. It'll be a team test, and you'll have an opportunity to update answers as we go too. So I will see you in the next video. Thanks for watching.